we've arrived at part 3 of the cells and cytology. And in this case, we're dealing with the varieties of diffusion that can happen, the passive systems, which do not have an actual active pumping energetic origin, but rely completely on kinetic energy. Okay, so when things move passively within a system, in order to move toward equilibrium, we're going down diffusion gradients and from high concentrations to low concentrations. So here we have a situation in which we want to move toward equilibrium, and in this case we have a U-tube, and I'm going to have my own version of a U-tube here in just a moment, but here what they've done is they've created a little barrier. Do you see that? And on one side they have a lot of solutes, and on the other side they have only a few. So the concentration of water is greater here, concentration of sugar is greater on this side. Okay, so the situation that we have here then is that the solute can move this way and the water can move that way, and that's exactly what happens, is that the solute can penetrate the semi-permeable membrane, and now you're seeing that the solute has distributed itself as well. The water molecules have engaged in random collisions, and the collisions have been more often at high concentrations and less often at lower concentrations. So we move through the percussion of these molecules from many percussions away to fewer percussions until we're evenly distributed. Over here we have a semi-permeable membrane that's gotten smaller, so now the solutes can't get across, and the solutes remain the same on both sides, and the only part that can move is the water. So the water moves from this side, where you could say the water concentration is high, to this side, in which you could say that the water concentration is lower. And so the water, in fact, does move, and now we're seeing a much more even distribution. The space between the particles is more or less at equilibrium. Okay? So I'm going to present you with a completely different picture over here. And this one, I've drawn the U-tube. It's a semi-permeable membrane. But in this case, we've poured in water and we've put something only on one side, protein molecules, which are very large. And the protein cannot penetrate the semi-permeable membrane, but water can move both ways through the semi-permeable membrane. So the only thing that can redistribute itself is the water, not the protein. So we have a similar situation, but I'm going to go through a more careful, how shall I say, notation of what's going on. So, as expected, the water moves from this side. As you can see, the water level is diminishing. It's moving away from this side and across, and I have a bigger arrow here for the water that is randomly moving this way, and a smaller arrow for the water that's randomly moving back. So water is preferentially moving over to this side. The protein, again, cannot penetrate. But what we've done over here is that we've diluted the protein. We've increased the water column over here. And through what pressure did we do this phenomenon? We created something called osmotic pressure. So it's the pressure of water. And this is the case wherever we have membranes in the body, capillaries, for instance, is that we have pressures based on protein. The blood is filled with proteins, very high concentration of proteins, especially albumin, and so water from the interstitial fluids move back into the blood toward the protein and away from the cells, and that's a clearing mechanism. Okay, so at the beginning of capillaries we can deliver nutrients in water, and then at the far end of the capillary, the hydrostatic pressure, osmotic pressure, rather I should say, the osmotic pressure is great, and we get the water back along with the dissolved waste products. In this case, we have a simpler system than we do in the blood and in the body. We just have these two molecules, water and protein. In this case, the water has shifted to the right side and has created a standing column. And so there's pressure in that standing column because the water has weight. We have the weight of the water, hydrostatic pressure, and it's going to come into balance with the osmotic pressure. The osmotic pressure is ongoing. This continues to be pure water. This continues to be dilute water. And so the pressure is ongoing. The pressure in terms of the weight, the Earth has an acceleration called gravity. Okay, and so we're going to have that force acting here, the weight of the water, as hydrostatic pressure. And so that's this situation here in which we have osmotic pressure now equal to hydrostatic pressure. So I've abbreviated that right here. When osmotic pressure and hydrostatic pressure are equal in their forces, then we have equilibrium again, and we remain in this scenario right here. Okay?